In this lesson, data center traffic flows, we're going to talk about data center traffic flow directions. In other words, how does traffic flow through the data center? And what types of traffic flows we'll see in the data center. We'll look at the separation of application tiers, and we'll actually take a look at an example of how we separate the application tiers in this particular lesson. And we'll describe what east-west traffic is and how east-west traffic can be secured, and north and southbound traffic and so on, right? We know that traffic flows obviously between our data center and external devices, all right? I mean, that would be the whole point of having a data center in the first place, is to have this data that flows from our data center to our external devices. So we need to learn how to identify what the predominant traffic flows are in the data center, and then we have to design a network that's going to fulfill our capacity requirements, our resiliency requirements, security requirements, and so on for these different traffic flow directions, all right? And that's what this lesson is really all about. When we look at data center traffic flows, we classify these flows in three different directions. We have north and southbound traffic flows, and that's traffic that enters or exits the data center. Typically, that's going to be traffic that flows between the clients that are located outside of the data center and the servers in the data center themselves. And then we have east and west traffic flows. That's between the servers or the devices inside the data center, and our east and west traffic flows are the flows that don't actually leave the data center. And then lastly, we have what we call the inter-DC traffic flows, right? The data that traverses those data center interconnects. You'll see references to these traffic flows on the exam, so it's important that you kind of identify where these flows exist. And when you're doing data center design and you're working with Cisco or working with other data center vendors, they typically will classify traffic flows in the same way, all right? Unlike in a campus network, where the dominant volume of traffic is typically, in a data center traverses in the east-west direction, in our modern data centers, 70 to 75 to 80% traverses in the east-west direction. Maybe about 15% traverses in the north-south direction, and then maybe 5% or something like that will traverse between data centers in the DCI, inter-DCI or inter-DC connection. Traffic volumes and the direction don't only dictate oversubscription of our data center topology, but also the position of our layer 2 and layer 3 devices and the border between layer 2 and layer 3. Strong north and southbound traffic means that we prefer a small layer 2 domain, and then we use inter-VLAN routing in the aggregation layer. If I have mostly east and west traffic, then that is going to advocate maybe a larger layer 2 domain with inter-VLAN routing at the core. So this is why we would be concerned with identifying these traffic flows in our data center, because it's going to dictate how we build this data center topology. North and south and east and west terms, we know that kind of is based on a scheme where the core is positioned at the top in the north position, and the servers are at the bottom in the south position. So it's stuff, obviously that we concern ourselves with. Now, we do have different traffic flow types, right? And it makes sense if we break them down, right? We've got client-server traffic, and that's typically going to be our north and southbound traffic that enters or exits the data center and flows between the clients that are located outside of the data center and the servers in the data center. To protect this traffic and to add efficiency to the communication, we're going to use firewalls, we're going to use the load balancers, and so on. That's going to add components to our east-west traffic between the appliances themselves and the servers and so on. Oversubscription of links between the core and the aggregation needs to be carefully planned so that we can make sure that we have enough bandwidth for the number of servers that we actually have in the data center. Server-to-server traffic types, those east and west traffic types, those are the ones that never exit the data center or even leave a layer 2 domain. All right, so it's going to flow directly from one server to the other. And if we have any scalability demands or we have any security demands in this case, we'll use appliances again like firewalls or load balancers in between those layer 2 domains, right? Now, typically, server-to-server traffic is some sort of VM migration or communication between application servers and their databases, state and transaction replication information between the servers in a same cluster, typical server-to-server type communication. The server-to-server traffic, when server-to-server traffic flows between servers in a different data center, we know that that's going to have to traverse our data center interconnect, right? So we have this inter-DCI traffic that has to be managed and tailored because typically our DCI link capacity is much, much smaller, much, much less robust than the typical capacity that we would have inside of our data center, okay? There is another type of traffic that exists in data centers as well. We don't really see it listed here, but it's important to kind of mention it, right? It's modern data center storage traffic, NFS, iSCSI, fiber channel over Ethernet. These are definitely things that we have to consider. Other storage protocols also, right? They're going to utilize the existing data center network for that traffic. We actually have 3 types of storage traffic that we would typically work with. Server storage traffic, which obviously is directly related to our storage requirements on our database servers, our servers in general. Synchronous replication traffic between different storage arrays, meaning that we're duplicating information back and forth between different storage arrays. And then we have that asynchronous replication between storage arrays as well, where we're just simply copying data in one direction, right? So that's server storage traffic. Synchronous replication. These are going to demand, more specific tolerances, right? Especially things like low latency, right? Or jumbo frame support, or maybe lossless Ethernet and so on. So they're typically kept inside our layer 2 domain. They don't usually transit appliances, but this type of traffic, this asynchronous or synchronous replication traffic, the server storage traffic, that's all considered still east-west traffic, all right? Because it is staying inside the data center, all right? When storage replication occurs between disparate data centers, and when we have to actually copy data from one storage array or one storage location to another in different data centers, we know that that storage traffic is going to have to go over our data center interconnect. Unless the data centers are close together, right, within 100 or 200 kilometers, the capacity of the DCI, the latency of the DCI, reliability of that DCI, it's not really suitable for doing things like synchronous replication. So typically when we have to synchronize database information or storage information over a DCI component, we're going to use asynchronous replication, all right? just note, standard Ethernet, we know is best effort, right? It's a best effort medium. That means that it doesn't have any form of flow control. Inside of an Ethernet frame header, there is no, I mean, we have a frame check sequence to do error discovery, right, using a cyclic redundancy check, but there really aren't any flow control mechanisms. So if we have congestion or if collisions occur, we know that we're going to drop Ethernet packets, and it's up to the upper layers then to recover that information. We have a set of network technologies like data center bridging, which is going to enable the fabric to support lossless transmission. All right. So we have to implement those networking technologies to make them suitable for carrying our SAN traffic. And that's beyond the scope of this class to talk about that technology. I just wanted to point that out. Obviously, we know you guys were already aware that Ethernet is normally a lossy protocol, right? Also, if we're doing synchronous replication, all the data that is committed on the first storage array gets synchronized to the second storage array. That's the whole point of synchronization. And that happens before the server actually gets an acknowledgement that the data was committed. And the difference between that and asynchronous replication is that in asynchronous replication, we commit on the first storage array, and the commits on that first storage array actually get queued and sent to the second storage array whenever we have available bandwidth or whenever it's possible to do that transmission. So we can actually see potential data loss in the first, for some reason before that queued process takes place, if we see loss on that first storage data array and so on. We're not replicating to both arrays at the same time, okay? So let's take a look at a case study and kind of see how this applies. The case studies have been a little bit anemic in this material, but we'll take a look anyway, all right? So we have a proposed network security model with a 3-tiered application, and it looks like we got web, we've got database, and we've got application information, we, you know, it's typical traffic, right? The servers in the web tier are going to provide public-facing services for applications. The servers in the application and database tiers, they're going to provide our middleware and back-end processing components. But the applications are meant to be accessible over the public internet, all right? Of course, that's the broadest scope of representation that we can have. So we have some security concerns about accessing these different applications, all right? Because we're using a network-centric model, which basically uses a traditional approach, we're going to use VLANs within our layer 2 domain to logically separate each tier of the servers, right? And then we're going to have inter-tenant communication. We talked about that in one of the previous lessons, that gets established through the routing that occurs at the aggregation layer. It's a fancy way of saying basically just routing between VLANs or inter-VLAN routing. This network-centric approach, right, lends itself to designs with some or all the services applied from the outside of the compute environment or the compute tier or the compute infrastructure. That means that flows between the VLANs get routed through the aggregation layer. And then traffic typically flows through the firewalls, the load balancers before and in between those application tiers. That's going to provide us that security function, right? That is a typical kind of network-centric security model. And it's a traditional approach. We typically think of, when we deploy these applications, this is typically how we think of deploying these applications. But what if we wanted to look at a server-centric approach? right? Where we have a virtualized server layer and we're using VMs and separate VMs and NICs and allowing the communication that way. With this server-centric method, we're going to have essentially VM NICs, and those VM NICs are going to be in their respective VLANs, and that's going to allow us to daisy chain the server tiers together, all right? Now, this completely relies, as you can see from the diagram, on a virtualized server layer. So we're leveraging a virtual switch, either in the VMware ESXi environment or maybe a Nexus 1000V, to classify and optimally redirect traffic flows in that virtual access switching level of our infrastructure. All right? Seems reasonable enough, right? But it is a little bit simplistic, right? The problem that we see is that the applications are a lot more complex. They don't necessarily follow this strict hierarchical traffic flow pattern, all right? Some applications are written to function as a database-centric application. And as such, it's going to have communication flows to our middleware applications, to our presentation applications, which is our web tiers, from that database core. Another problem that we get with this is really a common problem that we see in a lot of enterprise scenarios. Some of the application flows actually have to extend outside of the private cloud to some sort of work group external to the private cloud, like departments or organizations. So this traffic is going to have to pass across different organizational boundaries, even possibly site to site. The application tiers themselves have to be distributed, maybe logically, locally within a database or data center, or physically across multiple data centers, or even across an entire enterprise campus. All right? So we're going to get suboptimal policy enforcement points, and it's going to be very difficult to have a seamless and ubiquitous policy across the design. All right? That means that traffic is going to have to go through lots and lots of different firewalls, and then we're going to have lots and lots of source and destination pairs that we're going to have to secure in that environment. So it's not ideal, this server-centric topology. So there may be a case for it. You just have to be aware of what those limitations are. All right. Now, we did talk previously about what east and west traffic is. Now we need to discuss what we do to secure that east and west traffic, right? East-west traffic is, as we talked about, generally server-to-server traffic. But it still has to traverse up from the access layer through the aggregation layer if we want to enforce security policies, especially if we have different firewall devices or firewall appliances available to us at the aggregation layer. So it becomes kind of obvious that the traffic flow gets suboptimal in this case, right? Even because the servers themselves could actually reside as VMs on a single physical host, but we still have to send that data up to the aggregation layer for processing. So the traffic in that case has to flow from the physical host through the access layer to the aggregation layer, just so we can filter it by the firewall and then forward it back south down to the same physical host. All right? It makes more sense in this case than to apply security policies on the physical host with a virtual firewall appliance. And that's where the ASAV comes into play, right? The Adaptive Security Virtual Appliance. Or a VSG, Virtual Security Gateway. Both of those are VM deployed options for applying security, right? what these virtual firewall appliances do is that allows us to enforce policy to the inter-VM traffic without having to hairpin traffic to our physical firewalls at the aggregation layer, right? And we know that the ASAV pretty much provides all of the virtualized security services that a standard firewall would provide, right? Firewalling features, IPS, VPN, email security, web security, and so on. The Cisco PSG supports provisioning of security policies by creating trust zones. When you initialize or install different VMs, and during the instantiation of those VMs, we can apply our policies. The general goal here is to apply the right security services as close as possible to the actual transactions that are taking place, right? We still have scalability, we still have resiliency in the data center, but we get that efficiency by being able to apply those security principles at the virtualized server layer instead of at the aggregation layer in a physical appliance. All right. We can also achieve high performance of our virtual firewalls by implementing multiple virtual firewalls, however many we need. We can create hybrid deployments where we have physical firewalls that are an extension of our virtual firewall environment. We can provision and manage all of this information with our SDN controllers using APIC. That provides us the flexibility and the control from a central standpoint that we normally would have. So in this very brief lesson, we talked about different traffic flow directions, the north-south traffic flow direction, which is our client-server traffic that enters and exits the data center. We talked about our east-west server-to-server communication and inter-DC communication using the DCIs that we had talked about in the previous module. We talked about the need for planning for oversubscription, particularly with the client-server traffic that is going to go from the north to the southbound. The server-to-server traffic, for purposes of efficiency and scalability, we try to keep that within our layer 2 domain and utilize virtualized appliances so that we can keep all the traffic in the virtualized server layer. And then on the storage side, keep that layer 2 domain, apply some sort of lossless Ethernet technique, maybe utilize jumbo frames and so on. And then if we're doing intra-DC and inter-DC communication, synchronous replication has to be less than 200 kilometers. Anything over 200 kilometers would require asynchronous replication. All right, and that concludes that chapter. Next, we're going to move into SDN and how APIC works in the data center.